Okay, so this is a continuation of the last video, which was a review of Introduction to Statistics. This is about Simpson's paradox, chi-squared, and ANOVA. So you should understand the idea behind Simpson's paradox, and right now you're not expected to know how to compute chi-squared or ANOVA by hand or even on a computer. However, if you are listening to this and you are in my stats software class, you will be expected to learn that in that course. But as an outgoing Stat 202 student, you would not have been expected to know how to compute that. If I give you an output from chi-square or an ANOVA calculation, you can reject the null hypothesis, fail to reject it based on a p-value. So you can do those two things based on just the p-value and skip over all the details. And so that's the pitch level of this presentation. How are these ideas related? Well, Simpson's paradox is often explained using a two-way table. So this picture that I showed you before, and I'm going to show you again, demonstrates a different version of Simpson's paradox, but the picture makes a lot of sense. Generally, in the basic examples, we give Simpson's paradox in tabular format. And so we represent Simpson's paradox and also ANOVA in a two-way table. And so that's why students sometimes can't tell which is which. But they're quite different. Simpson's paradox, the thing you're doing is you're counting how many of each thing is in each category. It's just a nose count. And the ANOVA, the two-way table, is used differently. So we'll see some examples. Okay? So the thing is, with Simpson's paradox, most introductory stats textbooks don't really explain whether the results are significant. They just flag them as being Simpson's paradox or not. And I think that's really misguided. So let's talk about how these things are interrelated. Okay, first of all, Simpson's paradox, again, this picture is to give you an idea or a flavor of one type of Simpson's paradox. Basically, the underlying rule is if there's a trend which comes out in groups, so the blue group and the red group both show the same trend, but when you ungroup them, the trend disappears or reverses, then it's called Simpson's paradox. This often happens because of an unknown lurking variable. So here is an example where if you just, for example, look at whether the death penalty was given or not given to whites and African Americans. You say that, okay, 11% of the Caucasians receive the death penalty, and in similar situations, about 8% of the African Americans receive the death penalty. So first of all, you say just right off the top, more Caucasians are receiving the death penalty percentage-wise, but then you say, wait a second, is that even significant? So this is the problem here. We often talk about Simpson's paradox and we disregard whether or not it's even significant, this difference between 8% and an 11%. It might or might not be important, that difference. It could be sampling error. But just for the sake of argument, let's pretend it's significant and see what happens if we split by the victim's race. So in this case, if it's a Caucasian victim and a Caucasian defendant, then it's an 11% chance of the death penalty. And if the defendant is African American, that doubles. That's important to note. And the sample size is obviously really, really small for victim's race and defendant's race. When victim's race is African American and defendant's race is Caucasian. There's 0 death penalty and 16 no death. But you see, this is a very small sample size, so it's not really significant. It's not telling you that much. So that's leading me to believe that there could be some sampling error going on. But you still see that if the defendant is African American, the chance of getting the death penalty goes up. Okay, so how to use chi-square in StatCrunch. When you see data in a two-way table like this, whether or not you see Simpson's paradox, you should ask whether the numbers are statistically significant. You want to know whether the difference you see, in other words, even just if you just saw just the first table, is this difference between 11 and 8%, is that due to um, just sampling error, or is there real variation in the ratios? The more categories you use, the more careful you must be, because then you are more likely to get these empty boxes that are glaringly not statistically significant. So we will use small samples. Now, if we go back to this box over here, we have 53, 430, 15, 176. We're going to copy these down, and we're going to go in StatCrunch, we go Stat Tables Contingency with Summary, and then we select the columns we want, the row, etc. You can just follow the instructions here on these slides, but the point is we get this result from StatCrunch, and what StatCrunch does is it echoes back the numbers we gave. It does the row and sum, row total and the column totals, and it also gives you the expected count because I asked for it. Okay, so the expected count you can see is actually not that different. See, those are not that different from what we expected if there was no difference between the death penalty rate for Caucasians and African Americans. And so we don't have a significant result here. Now, it's possible that if we extended this study and took in more states or more years, we might have enough data to show that it is significant. But this particular set of data, just as it sits here, does not show any significance. Okay, so use intuition for small samples. We're often told not to use our intuition, but sometimes I think it's really important to use your intuition. In really extreme cases, whether it's extremely significant or extremely not significant, your intuition usually kicks in. It's the gray cases where you're not really sure if it's significant or not. Those times you really need to rely on the statistics. But for something that's really, really obvious, you look and you say, hey, wait a second. These numbers really don't look all that different. Okay, so this is kind of hazy. But for example, here where there's a 0, that is a glaring indicator that you don't have enough data. Okay. When your expected count and actual count are only off by a couple individuals, you should not expect the p-value to contradict your intuition and to reject the null hypothesis. So if you're only off by a little bit, you should fail to reject the null hypothesis. Okay, so how do you calculate the expected count? Okay, so this is what you do need to know how to do by hand. The total population times the probability of being in your row times the probability of being in your column. So in other words, we can skip a step by just saying the row sum times the column sum divided by the overall sum. So both of these two processes give you exactly the same result. It's just canceling one term. So in this case, Caucasians, death penalty is so the total of 48 Caucasians, total of 68 death penalty divided by the total of all the data set gives you expected value of 48.73. The actual count was 53. 53 kind of feels like 49 or 48. It seems about the same. So for example, think about this. If you have a room full of 49 people or a room full of 53 people, it feels roughly the same, especially if you know they were drawn from a pool of 483 people. Okay, so your intuition says it feels about the same. Okay, let's do the same thing for the split data. We split the data, the white victims and the black victims. The white victims are borderline significant. You see this p-value here is 0.02, so it falls between 0.01 and 0.05, which is what I've told my Stat 202 students is sort of the gray zone. If the p-value is less than 0.01, we can usually say it's significant in most situations. If it's larger than 0.05, we usually say it's not significant. If it falls between 0.01 and 0.05, we have some talking to do, and we really should have chosen our cutoff value before we got to that point. But I'll just call that the gray zone, or the borderline significant zone. The black victims, however, definitely not significant, and we knew that because we had a whole box with 0 in it. Okay, so that's a dead giveaway that this is weird data. Okay, but there is still a story to tell. What is significant is if you split this, if you say, okay, there's the same number of people, you say, okay, if there's a Caucasian victim, then usually the death penalty is what? Well, not usually, but it's more likely. And if it's an African American victim, then the death penalty is not likely. So this is bizarre, right? Because you would think that this would be the same in both cases. And these numbers are really, really small. But the p-value is saying, no, 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 these are actually really, really significant. The fact that this is so small is why it's so significant. So look at this. The expected count was 16, and we only got a quarter of our expected count, where for the African Americans, for the death penalty. But for Caucasian victims, it's roughly the same. You know, like 52 and 64 is roughly the same, but we got more death penalty than maybe we would have expected. But here, this is way lower than we would have expected. It's off by a factor of 4. So that's pretty significant. And this is exactly the point of the matter behind the BLM discussion. The statistics back up the fact that the culture does not seem to care if a African American person is killed, so they're more likely to let the supposed killer go free. But if a white person is killed, then is more likely to say, hey, that's not right, we're going to punish you. So this is definitely in support of the BLM discussion. And this is statistically why ALM completely misses the point. We're saying, no, look, black lives should matter. You see right here is telling us that the juries are not convicting at the same rate when it's an African American person who was killed. Okay, right, back to the statistics. ANOVA and chi-square. Chi-square is looking at proportions in two-way tables. You are comparing group proportions. However, ANOVA is looking at continuous measurements in 2 or more groups to see if they are different. It's like a massive t-test for more than 2 groups. Now, it's fine to use ANOVA if you just have 2 groups. So if you understand how ANOVA works, you can basically throw away your t-test. I didn't say that out loud, did I? Yeah, maybe I did. Okay, so the point is you're comparing group means. What does it mean? It means analysis of variance. Okay, recall our t-test questions. The standard questions we use involve student performance. We had a question earlier about 2 groups of students and their SAT scores, but what if we wish to compare multiple groups? So in an old exam, I had this question, SAT score with 3 subscores, and presuming, incorrectly of course, that there's no correlation. The overall average, you just add these guys up, 525 plus 525 plus 545. And you get 1595. What's the overall standard deviation? Well, you have to square each of those. So you get 3 times 100 squared, and then you take the square root of that, and you get 173.2. Sample size is 64. Okay, so we're going to have a sample of 64 students, and the question that my students had to answer is we have 2 possible folders. The names have been blacked off, and we want to know one of the folders is for this school and one of the folders is from another school. And the sample mean of the folder you grab has a sample mean of 1525. And the question is, how likely is it? Somehow, is it likely that it came from the first school? And it's not remotely likely. Because you have to take this standard deviation and divide by the square root of 64, which is 8, and then get the standard deviation for the sampling distribution. All right, so anyway, this is really, really unlikely. So it's in this type of setting. Let's compare SAT scores of the incoming first-year students for all area universities by taking samples. So let's imagine you can go into each local campus and randomly ask students what their SAT scores were. Yeah, right. Of course that's not going to work. We're going to pretend. So what you want to know is whether there is any statistically significant difference between the schools. So this is completely made up, bogus data. For each of a variety of schools, you walk up onto the campus and you ask some students randomly, what was your SAT score? And you get some answers from AU, George Washington, Harvard, yeah, that's a local school. TC3, yeah, let's just do that. And here's the box plot. Don't neglect your powerful low-level tools. Your intuition does mean something here, and realize these are very, very small samples. So what do these mean? Well, it looks like Harvard is way out there above TC3. It looks like maybe AU and GWU may not be that different. I mean, again, we have a really small sample size, so I'm not really sure this is going to be significant, but I suspect that this difference is going to be significant. That's my guess. Let's see what the statistics say. We do one-way ANOVA to test for different group means. So you do stat ANOVA one way, you just do this in StatCrunch, and you select your data, you do your Tukey test, and what do you get? This says the p-value is significant. What does this say? Right here, this p-value says significance. However, when ANOVA comes out significant, it doesn't tell you which groups are different from each other. So it's basically meaningless. Well, it's somewhat meaningful, but it doesn't help. So you do Tukey and you say, okay, which ones are different? And you say AU subtracted from Harvard is kind of significant. That's in the gray zone. Okay, and we see GWU, George Washington University versus TC3. That's kind of borderline significant. But whoa, Harvard subtracted from TC3, that's super significant, which is exactly what I said over here. And it's saying that this difference between TC3 and Harvard is wildly significant, and some of these other differences between Harvard and GW and Harvard and AU, they're kind of like in the gray zone. But AU and GW, they're not different. Let's see. AU and GW, yeah, that p-value is really high, so not significant. Okay. So Tukey says actually pairwise, no two schools really are different except when you directly compare TC3 with Harvard. The others are either insignificant or they're in the gray zone. Okay, so this is about my Stat 202 final. You don't have to worry about that if you're in my statistical software class. But you should be able to, everyone should be able to look at output that is generated and explain in plain language what the results are saying. For a very low p-value, there's a highly significant difference between groups. If it's high or marginal p-value, it's inconclusive. Or you might argue for a larger sample size, especially if you're in the gray zone. You might say, hey, with a larger sample size, that would push that either into the inconclusive category or it would be conclusive. That's usually my line of reasoning.